I'm MC Toon, and it's Tuesday night. That means we've got a debate or a conversation. Maybe this is more of a conversation than a debate. This is between Robert Greenlee, who is on screen right now, and who is if you know him from Facebook, he is not a flat earther. He's a globe guy, a pilot, and Bradley, who just sat down there. Welcome, Robert and Bradley. How are you guys doing?
Doing good.
Well.
Why don't you each take just a minute to introduce yourselves? Let's start with Robert. Just quick, what you think?
Many of you know me. I've done a couple of online debates. For the most part, I do a lot of Facebook conversations around the topic, but occasionally they get me on camera, and I kind of like it because it makes you think on your feet, and you're not just reading off a script or copying from Google. So it's kind of fun to do a live debate. But as the MC Toon knowledge, I'm a IT guy by trade, but I'm also a private pilot. So I've been flying, for about 17 years now. So that's my hobby. I would call it my stress relief. So yeah, we're kind of hoping to have a good conversation tonight. That's not necessarily a debate, and definitely not a dumpster fire. We don't want to hear that. But I think we'll both have some things we want to bring up, and we'll discuss it, and we'll see how it goes.
Awesome. And Brad?
All right. Yeah. So this is a while that I'm here discussing this with you guys. I got into kind of this rabbit hole in 2016. Put it away for a while, but a friend of mine started a podcast, and it was a topic they're interested in going over. So I jumped on the podcast with them, and now here I am. I'm not a pilot or anything like that. I did take, physics and calculus, chemistry in college. So, I have some basic understanding. I'm not, a professor or anything like that. So I'm just probably like most average people that are trying to look at this topic. Coming into this, I'm a globe believer. And at the first time I came across this topic, pretty much just wrote it off. I mean, you don't even give it the time of day. So what's been a lot of fun for me is opening this up, seeing how much depth there is to it, far more than I expected. And that's, why the discussion really excites me. So thanks for having me here.
Awesome. Well, I will hopefully just have not a ton to do of this other than just facilitating. And if you guys have some things you want to present, I can get them up on screen for everybody to see. So I'll let you two just get going at it here.
Yeah, so I thought maybe we would kind of, I'll present a topic, you present a topic, or you can go first, and we would just kind of discuss it, see what you think. Obviously, I do bring my pilot background, so I think I mentioned I'd probably show something related to, aviation and navigation. Kind of have to ask your opinions on certain things about that. So would you like to go first? Do you want me to go first?
Yeah, go ahead, take the lead.
Okay. Well, I am curious. Are you familiar with the Sydney, Australia to Santiago flight?
Somewhat, yeah.
Yeah. So it is one of the, not the longest, but it was actually for a while. It was, but one of the longest nonstop flights in the world. And this is kind of a show you a graphic of what it looks like. I'll share out my screen real fast. Give me one moment. I want to share my other screen here. Once it comes up, and I'll wait to make sure that I'm seeing it on the video before we go. Yeah. So what I'm using here is a product called ForeFlight. It's probably about the top third aviation planning tool. Not only is there a web-based version of it, but it's also on, it's on my iPad, it's on my phone. So I've kind of got a triple redundancy. When I'm in the cockpit, I can navigate off the onboard avionics. And if that failed, I can go to my iPad. If that failed, I can go to my phone. So it's kind of triple redundant, but this is used by, probably tens of thousands, if not more, pilots around the world. I'm showing it to you here on my iPad. And so that's basically, here's Sydney, Australia. And this is the direct flight path from Sydney. And you'll notice they're kind of coming across, it's coming down pretty close to Antarctica, and then coming back up again. And I can see up in, I can't, first I have a like pointer, but It is 61,035 nautical miles. I kind of gave it a fictional aircraft here. The flight typically takes about 12 and a half hours, depending upon the winds. I only have it flying at 15,000 feet, so I think it's creating more wind resistance. I'm not a high altitude commercial airline pilot, but it's kind of stuck some numbers in there. If I adjusted that, it would probably change the time a little bit. But this is the direct path going across the globe. If I looked at it in a 2D representation of it, let me bring this over into here. This is kind of the desktop version of the application. You see that classic kind of great circle route where you see it dipping down south. And that's just the 2D representation versus the 3D representation when you actually look at it on an actual globe. So this flight, again, is about 6,235 miles, 12 and a half hours, easily within the range of a 787. If we take a look at that same flight, and give me a second while I go find that graphic. I made an attempt because, as you know, we don't really have an accurate flat Earth map. A lot of people like to use Gleason's. This is kind of a common representation. So all we can do is extrapolate. So I knew that on the globe, 635 nautical miles. I know that LA to New York is 2151 nautical miles. So let me just try to extrapolate and go through and say, well, how long would it be on this map? And it added up to be about 5.6 times longer, or 12,214 nautical miles, roughly, because again, I don't have an accurate flat Earth map. That would be a longer flight than any aircraft in the world is able to fly nonstop. And for them to do it in 12 and a half hours, the aircraft would have to be flying at Mach 3, which again, no commercial aircraft are going to be doing. So kind of curious on your thoughts of this flight and the comparison between the globe Earth and the flat Earth.
Yeah, that's a great question. So I've dabbled into the flight patterns. That's not really the strength of direction I've gone in. I know when a family member flew to South Africa, when they told me the flight plan from Washington State, it kind of surprised me until you did actually put it on this map. And then you have the story of the lady that gives birth on a flight from like Taiwan or Japan, and then lands in Alaska, which didn't make sense on the globe until you looked at it, on the flat map. Now, and I know you have the great circles, you have to visualize these routes a little different on a globe. And, the Flat Earth Camp will also point out that anytime you have a globe in a classroom, it's really for demonstration purposes because it's not accurate. I think it's you could Google the most accurate map in the world. They basically take everything into triangles, fold it all up as much as they can. It's like a 92 triangles to make a globe. And it's said to be the most accurate globe. It's kind of a flat map converted, and I understand that it's because projections, it's a complicated process. Yeah. But what I'm getting at is, is this representation of the globe 100% accurate that, for this flight, plan, is this not distorted as well? I mean, the whole angle with, what's the most accurate map? I think the triple map now is allegedly the most accurate. It's like you flip a coin, you have the north hemisphere on top and the southern hemisphere on the bottom, and it's still a flat projected layout, almost like the UN logo. But rather than having it taper all the way out with a ring, they on the bottom side, bring it back down to a point, like the North Pole, but the South Pole. So that's kind of interesting.
Yeah. So just a quick point on accuracy. This is based on the WS 84 standard, which is accurate down to 3 centimeters. So it is extremely hyper accurate, and it really needs to be, because when we were talking about, especially an oceanic flight where they're crossing 6,000-7,000 miles over water, if it was inaccurate, as you kind of saw that difference, almost many times longer on a flat Earth map, that aircraft would be running out of fuel. So the path wouldn't, even if it was off by say a couple hundred miles, maybe the flat Earth is a couple hundred miles longer. Okay, maybe they can get away with it. But when it's 5.6 times longer, it simply is impossible for it to be transferred to a flat Earth map. But let's talk about the scenario you're talking about with the Alaska flight. So give me the details on that one. Let's take a look at it.
Well, I'd have to Google it.
I think it was something like Taiwan
It'll pop
to
right up.
maybe LA, and they stopped in Alaska.
Yeah, yeah.
Yeah, so let's take a look at that one real fast. So I'm going to just kind of bring up a new tab here. First,
Oh, and
Taiwan.
another thing while you're doing that, the funny thing, with the flat Earth camp, they always like to talk about how, man, you can't go past the 60-degree parallel. You'll get turned around and all that stuff. And there's supposedly reports, earlier maritime days where they'd get further south, and the reckoning that they'd expect was not what they were getting. They were further off course than they expected. And the flat Earth camp would say, well, that might be because you do have the UN projection, this azimuthal equidistant map. That's how it looks. And if you try to imagine it tapering back down, you would be off course. So I guess it would be nice to have the full to have the southern hemisphere actually truly open, but that's just conjecture, I guess.
Well, I mean, the part of the problem too with you always hear them talk about that it's impossible to go past the 60th parallel. And then when you ask them, well, where does it say that? Oh, it says that in the Antarctic Treaty. Okay, where does it say that? And they can never come back and show you where it says that. And yes, we know that if you're a resident of, say, in the United States, you have to go to the State Department and say, hey, I would like to go travel down to Antarctica. This is where I'm going. This is I'm planning on doing it. And you fill out a form, and then I think they heard a couple of weeks later, they're like, okay, you've got approval to go do this. Stay out of these, environmentally sensitive areas. Away you go. So nowhere does it say that you're not allowed to actually go there. That's a
Well, no,
misnomer
and
that you can't do
yeah,
that.
in fact, and that is true. I mean, you can apply for an expedition. As I understand, the rules are extremely stringent. I mean, you can't. You have to pack your own excrement out, so all your own food in,
Agreed.
can't touch the land. So that really limits the
Yeah.
the explorative measures. But
Yeah. All right. So here's that flight from Taiwan to LA with a reroute to Anchorage, Alaska. So you basically see we're flying along, and at this point in time, so, say they're anywhere inside of here, if they have to divert. So if I'm flying, I'm just going to make sure that I'm looking at the screen. There we go. If I'm flying right about here and I need to divert, you can see that it's closer to go up into Anchorage than to keep on going into LAX. If
I think
we
it
were
was
to look
Hawaii was the other idea.
correct.
Well,
Let's see if I can find. Let me add Honolulu.
here,
So let's plot Honolulu in here.
let me share this screen with you real quick.
Yeah, one second. Let's add Hawaii first.
Only
And
one
then
can share at a time. Give them a second.
Gotcha.
Yeah.
Okay.
We know Honolulu's like KO code up top there. There it is. PHNL. So let's add on PHNL just so we can see what it looks like. Yeah, so that's about intersecting right there. So it is a good question of, actually no, so Honolulu is actually quite a way south. So you can see they would have had diverted either quite a way south or go up north into Anchorage versus continuing on to LA, which is even further away.
Yeah.
So on the globe, it made sense that they diverted off into Alaska, which is the closest major airport along that path.
Okay.
So I'll stop sharing and I'll let you share for a second.
No, that's cool. Yeah, no. I really, it's really cool you have that tool to use, especially as a pilot. So that brings a lot here.
Yeah.
Let's see if I can share this.
All right, I'll stop sharing.
Okay. Application, practice that. Okay, so I guess what I'm looking at is
Still there?
Yeah, it's actually kind of skewed what you're looking at, but yeah, we're kind of looking at like a web search.
Yeah, I think he.
Oh, we lost you for a second there, Brad.
okay. Yeah, I think something weird happened. Too much.
It unshared your screen too. So.
Okay.
Yeah, reshare.
Let me see if I can find you guys. Okay, so anyway, just real quick. So in this example, and again, they use this for the aviation logo, the UN logo, geological logo. I
Sure.
mean, this flat Earth projection seems to be extremely accurate closer in. I'm not sure what happens as you get further south, but that makes a lot of sense. Like I mentioned, when my family member flew to Africa, that also made sense. Because on a globe, it actually looks like you'd want to take that direct Great Sukul route straight down to the tip. But when you look at it at this projection, the actual way that the airlines would take you with, I think it's a stop in like.
Yeah.
Uh,
And you actually are correct that in the northern hemisphere, the AE map, even though it distorts, isn't as bad as in the southern hemisphere. The southern hemisphere is where it starts getting grossly distorted in the longitudinal axis because it's having to stretch it out further and further and further. I mean, that's why when you look at, and I don't know if you want to look at that AE map again and look at Australia. I know we got people in the audience. I haven't personally gone to Australia, but I know a lot of people who have. And Australia is definitely not 3 to 4 times wider than it is tall. It's grossly distorted.
Yeah.
But yet, when we look at it on a globe map, it actually looks, like it actually is.
Well, yeah, it's interesting because you really do. Every map is either going to distort size, shape, or I mean, there's no, especially on the flat map. But again, they don't really have a globe as precise. I know you showed me your software, and you said that's within 3 millimeters or whatnot. But so far they have yet to be able to transpose that directly onto a globe that you could put in a classroom.
What?
Well, at that point too, is it required to have millimeter level precision on a globe in the classroom? Because if you're looking at that scale and what you're looking at, I mean, say the scale of that globe is 25,000 miles around. For the same reason, people are like, well, why don't you navigate using a globe? Oh my God, the scale is huge. I mean, if I'm traveling from LA to Colorado, which is this, I don't need a globe filling the cockpit like this. I need detailed maps of that particular route that I'm going, which is only a very, very small part. So the scale of trying to navigate with a physical globe is just not realistic.
And early days of piloting, I mean, you had radio towers, and you were trying to line in on a particular tower that you know where it's at.
Yeah, they use radio towers. Have you ever wondered as you drive through small towns why the name of the town's written on the side of the tower? Mm-hmm. So that the pilot flying by could dip down. Oh yeah, I'm near.
Now, how far of a distance can you detect a radio tower? So you're flying. At what point will you be able to?
It depends on altitude. So
10,000 feet, private, right? You're a private flyer. So
private pilot. So let's take a VOR for an example. So a VOR is I'll show you an example of what one looks like real fast because they're kind of goofy looking things. Give me 1 second here. Here we go. I got to share out my screen here real fast. Share second screen. So this is what a VOR actually looks like on the ground. It's like, God, I can now just drill blanket what the hell a VOR stands for. It's like omnidirectional radio. It's sending out the beams all the way around it. And what the aircraft picks up is that it can actually detect, like, okay, I'm on the zero radial beam coming off of that VOR, which tells me I'm directly north of the VOR. And then the DME equipment can tell you, okay, you're not only directly north of the VOR, but you're 30 miles away from it. And one of the key things with the VORs is we have low altitude VORs and high altitude VORs. So obviously the low ones are kind of for little airplane pilots, but you have to jump from VOR to VOR to VOR. Let me see if I can find a VOR map here. Now, and the reason you're doing that, here we go. I need something bigger than this. Come on, Microsoft. I need something bigger. I need a bigger one. Oh my God, that's even worse. Let me sort by size, filter by.
Do you want like a VFR chart?
Yep. Oh no, I mean the VFR chart will do it too, but there you go, something like that. So each one of those are actually, you can kind of see it. You see these lines where they converge. I want to find a better one because that's still not what I want. You know what? I can actually do it inside of here. One second. I think I can do it inside of here. We'll just do it from the webpage. But anyways, they've got VORs all over the country. And the reason they do that is that you can't pick one up. Well, let's take this one. So let's just say these are VORs. These are actually airports, but we'll say for conversation's sake, they're VORs. So as I'm flying along, say I tune into this first VOR as I get within range of it, and I fly past it, and about halfway across that airway, I'll then tune into the next VOR, pick it up, follow it along, jump to the next one, jump to the next one. And the reason I do that is so that I can't pick up the one that's way out here from back here because the range isn't good enough. Now, one thing I can do is if for some reason I wouldn't want to be flying along at 500 feet because it really limits the radio range across the curvature of the Earth. So I can be flying along, climb up another 1,000 feet. And this is especially true with the actual radios we use to talk to air traffic control. Is a lot of times if I'm flying along and I can't reach ATC, I'll just climb up another 1,000 feet and I'll be able to pick them up because now I'm getting that direct line of sight connection back to the air traffic control radio signals. So altitude makes a big difference in the range of the radios.
Yep. Well, you said,
question.
Yeah, and you said, keyword. I mean, these are line of sight towers.
Yes. Yep.
Okay. And so when you said they shoot beams, they're direct. I mean, it's not like it's emanating. You have direct beams, line of sight. Correct.
Correct. Yeah. It's basically I wish I understand the exact technology, but yeah, it's basically sending out a radio beam every 1 degree. So then the equipment on board the aircraft will pick up. Okay, you're picking up the 180 beam, which means you're directly south of it.
Right, and then you can align yourself to that beam because you know the distance you are from it, right?
Yep.
Is that how that works?
And,
okay.
Yeah, there's two ways we can. If you have DME equipment, which is distance measuring equipment, it's really handy because then you can plot out and say, okay, I'm on the 180 radio and I'm 50 miles away. Oh, I'm right here. But if you don't have DME equipment, say I'm flying along and I'm coming in right here, I can dial in. I've got two navigation radios in the aircraft. So I can dial in this VOR and this VOR. It'll tell me, okay, you're on the 180 radio on this one, you're on the 0 radio on this one, triangulate it on your map, and now you know where you're at.
Okay, so what's really cool about what you're talking about here is line of sight. And, I kind of stumbled into, this part of the argument for the flat earth camp too, because, like I said, when I started this whole endeavor, it basically, it was like we're in the 20th century. Who on earth thinks the earth is flat? This is stupid. Once I gave it the time of day, the nice thing is I learned more about my world, right? So I want to get into optical stuff. I want to get into refraction with you too. But what's really interesting is microwaves, these radio transmissions. It's how, for instance, that they say the ISS communicates. Most all the cell towers are backhauled with microwave transmissions, and they're all point to point. And there's a definite limit on how far you can project it. The further they're trying to push it, the worse actually, the slower the data transmission is because they've got a band to work with. So,
Right.
They can do short with lots of data. But what's interesting is they can achieve up to like 156 mile here. Let's find the, I can share this with you. So these line of sight microwaves or radio frequencies, you can actually omit refraction because they don't refract. And then you can actually do these line of sight tests. Let's see, where did I put these?
I took a look at one you were talking about the other day. Give me just a second to find it. Actually, I can actually copy it. Where did it go? Come on. You got way too many web browsers open up here.
Oh yeah.
Yeah, but I found that one pretty interesting, so I started taking a look at it. It was like from like Chicago area up into Canada, something like that.
Yeah, and they make mention that they can get the highest distances over water, and which would make sense because if we're talking zero obstruction, that's probably one of the best places you can get, especially on a flat surface. But if it's line of sight, there's you really have a hard time trying to explain away these results with refraction. And nobody has ever said gravity bends microwaves. In fact, that's the whole nature.
So this is the article you posted, right?
Let's see. Right, that's one of them. Yep.
Yeah, so I looked at the first scenario. So they're basically saying going from Whiteface Mountain in New York to Mont Tremblant, if I pronounced that right, in Quebec, which was about 133 miles. So I'm like, okay, let's take a look at that. So I brought it, excuse me, brought it up in Google Earth. Oops, come on, Google, cooperate. So here's Mont Tremblant up here. And it's actually the mountain itself is where that pin is at. And then here's Whiteface Mountain. So let's measure it. And here, where'd the measure? There it is. Let's take a look at, I'm going to do it one more time because I wanted to show the elevation profile. So 134 miles, what I got, so pretty close to what they said, right? So here's the 2D representation, obviously now with curvature of the Earth. So you can see that they could pretty easily, no obstructions along that entire path using the 2D model, but we're not in a 2D world, or at least that's what we're debating. So let's take a look at it in the curvature calculator. And I'm using, where'd it go? Advanced curvature calculator. Because what it allows me to do, a lot of curvature calculators, they ask you, how high up are you and how far away is the target? But the problem with that is it's not factoring in the distance or the height of you and the target. Because obviously, if we're down here or up here, you got to calculate both of those. So I told it.
Usually, so like it'll tell you like obstructed portion. You can kind of infer.
Exactly.
Yeah.
So I put in here the first mountain near New York is 4865. Now they didn't say in their article how high up the mountain they are, but I just I put it at the top of the mountain, 135 miles away. The mountain in Quebec is 3,058. I could do standard refraction, or I could take away refraction totally, but I just kind of left it in there for now. So looking at this, there's 2,000 feet of that mountain out in Quebec still visible using standard refraction because of the fact. Now, if I change this and say the target size is now only
and I'm glad you clarified using standard refraction. So
yes, yeah.
But
if I take away refraction totally, refraction is 0.
Okay.
I'm still seeing 85 miles. I'm sorry. Still seeing 1,400 feet at the top of that mountain in Quebec with 0 refraction.
Okay, so I'll have to go back and look at my calculations because it actually there was one from California to Hawaii.
Let's finish this one first.
Yeah.
All right. Let's talk about this one first, and we'll talk about Hawaii because that was really interesting.
Yeah.
So at least you see.
Well, because just so we can agree. I mean, if obviously we're doing microwave transmission, so there is
correct.
A refraction, right? Okay.
Yeah, I mean there is. Microwaves do refract a little bit, but I agree. Generally, they're line of sight. I mean, as soon as you start adding refraction, then you start losing signal quality, which means you can't send as much data.
Well, you can deaden the signal through a bunch of fog, right?
Yeah, exactly. Yeah, so,
but it's not actually.
Yeah.
As far as I understand, everything I've, microwaves don't refract. So.
And that's why microwave towers are generally just like the VORs we were talking about earlier. They have them kind of, every 50, 100 miles, so they can bounce the signal from one to one, because it's not possible for them to send it, all the way across the United States because, the Earth is curved.
Well, actually, it's because there's limits to microwaves.
Actually, microwaves go pretty darn far, but.
I mean, we so here, let me share this when I get it to you, because
yeah, I'll stop sharing.
Let's see here. Just talking about some of these microwaves here.
By the way, not to make you nervous or anything, but there's about 300 people watching us right now.
Hey, no, that's great. The thing is, there's plenty of people online willing to have this debate. I mean, it's almost astonishing that it's you know, you could get lost in conversations, wind up with multiple conversations. And I kind of want to touch on that too, because I know there's a lot of people like yourselves that are out there getting frustrated with all the people that are believing the earth is flat. And the conversation degrades to insults really quick. And then it also goes the other way. So actually having a really open forum, it gets difficult. So,
Oh yeah.
but it's really interesting. So anyhow, this is let's see if I'm in the right spot. So we believe, so the microwave systems deliver the highest performance and reliability, and this deployment proves that, let's say CEO founder of Exalt Wireless, we believe that the previous distance record was 225 kilometers. That was overland using dual radios at each end of the link. So the deployment uses just one radio at each end of the link, and we link it over water, which creates significant transmission problems for ordinary microwaves. So they're talking about how they have a way to boost the transmission and get more range even over water. So
Okay.
you know, that's real fascinating, because, you know, the closer you are to the surface with the line of sight, the higher the receiver is going to need to be. And if you punch in 225 kilometers to the Earth curve calculator, you know, you start, you know, trying to figure out what kind of challenges they have. But
Well, that's 135, just for comparison, 135, they call it 140 miles.
mhm.
You've already proven that the one going from New York to Canada at 135 miles is easily possible. So that 225 kilometers isn't really outside the realm of, hey, that shouldn't work on the globe.
Right. Well, it got me looking at high-end microwave emitters. You know, I've got the camera coming, the P1000.
Nope.
And anyway, but they're like $25,000 or something, so it's probably not a toy
Oh
I'll get
yeah,
anytime soon.
that's some pretty high-end stuff.
Maybe I can jerry rig my Panasonic.
Yeah.
Let's see. So this is just talking about up here at the very top. Oh, that probably wasn't the one. Here, I'm going to unshare this right now. But the microwave issue is there, and then there's the refraction, and I'm glad you talked about that, because, you know, at first glance, you know, you have a lot of people, you know, and I think, in fact, that's what really drives most of the issue with people that are really saying, look, the earth is flat. If you go out there and optically record it, the earth is flat. The only way that the earth becomes curved now is when you put the refraction quotient in there, because now you can say, well, mathematically we have a curve, even though optically it looks flat, and the math works out. But time and time again, people are coming out with these cameras and just doing a lot of work, and there's numerous ones out there. I've stumbled across DuckDuckGo, and I was surprised when I typed in these conversations, or I mean, the flat Earth stuff on DuckDuckGo, what came up that didn't come up on Google. So, you know, my friend Brian, who didn't make it tonight, you know, that's he wants to be an observer of this topic. You know, he just barely got into it, and he says, you know, the fact that there's a shadow ban on this topic, it's really fascinating to me, because, you know, why is it so censored? You know, we live in an information age. You know, I guess people just aren't trustworthy enough with the information, so that it gets censored. But that's another topic.
What do you think of the shot on my screen?
That looks like a curved horizon.
Yeah, so this was taken by a friend of mine, Hans Baldwin. Until the pandemic happened, he was an airline pilot for Vietnam Airways. He actually lives down in New Zealand. He took this out the front window. If you ever look at a front window on an A320, it's just a flat pane of glass. There's no curvature to the glass. In fact, it's required by regulation that out the front windows of an airliner, they have to be optically pure. So there's no distortion from the front windshield. He took it using his Android cell phone. So no special, you know, it's not a GoPro. It's not some fisheye lens. It's just his standard cell phone. And he said this kind of matched what he was saying. This is, I think he said, about 41,000 feet flying towards Vietnam. What really helped out is the fact that the sun was just starting to come up to highlight the horizon. There's no clouds kind of blocking the view. Because a lot of times when you see Tony will post a picture, look, there's no, you know, there's no curve. Well, and then the sky is full of clouds, and you can't actually see the horizon. So that's one that he took. This one here.
So how many miles? 41,000 feet. What? That's 8 miles.
Yeah, I had to do the math too.
Something like that. Close enough.
Yeah, 41,000 divided by 5280. Yeah, 7.75 miles. This is one I took. I think I was over Idaho at the time. The sky was pretty clear. The curvature really isn't apparent here, but what I wanted to point out is this was using a theodolite, I'm probably pronouncing that wrong, tool. You notice it actually took me about 12 shots to get this so that everything was zeroed out. The camera's perfectly level. I didn't have any pitch to the camera at all. It's all 0, 0. So that crosshair is straight out level from the aircraft itself. If you notice, where's the horizon at?
Well, that is, again, that appears to be a curved horizon, but also the horizon is really, it's not evident in this photo.
Well,
exactly where the horizon is.
Yeah, well, we definitely don't know. I'm going to just take a screenshot of it so I can draw on it here. I mean, we can kind of draw, I can tell you where I think it's at, but we'll kind of compare. You can see the Earth here, and I actually kind of showed a little bit of curvature, but I was only at 35,000 feet, so that's hard to see curvature that low. But the key thing we're looking at, obviously, the horizon is not way up here. I mean, you've got these real thin cloud layers. This is where you start seeing Earth down here.
Yeah, I think the horizon, personally, because I've watched a lot of these videos where they dissect it, and it's really interesting as you get out further into the horizon, especially when there's a lot of clouds and possible refraction there too. But I would put it somewhere in the middle between the center hash mark and the solid red line you have.
Yeah.
And if you look to the right, up a little more, there's almost like a white band up a little more on that.
Yeah, the white band is clouds.
There's almost a white band, that does look like a cloud, but it's hard for me to tell. But let me share this with you. It's a little bit of a shock value thing. I don't mean to.
No, it's fine.
But
honestly, I love that you're sharing things back and forth, because typically we do these is like I'll spend all of my time sharing, and then the other person will be like, no, and they won't have anything to share. All right, so McNeil deGrasse Tyson.
All right, so this one here.
What do I say?
Okay, well, it's really funny if you're going to disown him. That's okay.
I am going to disown him because he says a lot of stupid shit.
Well, that's, I think, probably one of he's his own worst enemy then, because
he is.
When he gets up on stage and tells, all these people, like Felix Baumgartner, there's he's talking about him, and he's like, gosh, they show this picture of the Earth curve in the background at 63 miles up, but that's just because the truth would be really, it'd let you down. Because it's flat, and he's numerous times brought that globe out and showed, you were only 2 millimeters above the ball, and so this is where the cognitive dissonance starts really hitting people, because now, shoot, how far up do you have to go to see the curve? That is a question I'd really like someone to put a solid answer on. Because this is national publicized televised stuff. He gets plenty of time to talk on Discovery Channel and whatnot as a physicist, and this is what he says.
Well, I'll give you a basic guide if I can share again real fast. And I found this to be, I'm sure it's not absolutely perfect, but I found it to be fairly accurate. And I'm not a fan of memes, but obviously from the beach, you're not going to see it. You're just too low down. But commercial flight, if you notice what it's showing, this curvature is pretty darn close to what I was showing in my image. Now, this is 5,000 feet lower, so mine was just slightly more than this. But this is about what you expect. Even at 72,000 feet, where Baumgartner was at, it's still not, if the sky's not clear, it's going to be hard to notice it. It's still not a massive amount of curvature. It's not until you start getting up to about 100 kilometers, 62 miles up, that, wow, now I'm really starting to see it. And I think that's what Tyson was trying to do, is it's not really apparent to you until you start getting up around that 100-kilometer range. Down here, if the sky's not clear, there's clouds in the way, it's going to be kind of hard to see. And I agree with him there. But generally, his pear-shaped Earth and some of the other things that he said, I'm like, oh my God, dude, you're just shooting yourself in the foot.
Right. And so I think this only fuels the fire, obviously, because you have like the Joshua Nowicki, everyone knows about that Chicago skyline and national television. Now this is a mirage because you shouldn't see this, is what he says. And if the conditions are just right, and that's how it always works, the conditions have to be just right. But what's interesting is, I have some questions about refraction because they say you have a 1.11 degree gradient every meter of or whatnot of altitude.
Yeah.
And if all conditions are just right, you can put like a 15% quotient in there. It'll flatten that out. But time and time again, we don't see that. And what's curious too is when you're looking out on the horizon and it's perfectly level. Like here, let's see. I've got.
Yeah. But real quick, while you're looking that one up, this one was just sent to me by Anton. God, I'm going to screw up his last name. It's Tampere. He's another airline pilot friend of mine. So he took this photo. He's in the chat right now. This line across here is the horizon line. It's just from the HUD. So that is perfectly level at 40,000 feet. And you can see the horizon's very, very clear in this case. Even though you got a cloud deck, it's pretty obvious that it's quite a ways below level. So this one's a clearer shot than the first one. I've got actually quite a few of these that he sent me over time.
Okay, so what are you showing me with this one again?
So this is the heads-up display. Let me ask him what plane were you flying? He'll tell me which jet he was flying. So he's the pilot flying this aircraft. You can see it's at 40,000 feet. This line across here is level. That's your horizon bar. Okay. And then you see where the horizon is down below that. This is from the Airbus A220 he was flying.
Oh, cool. Yeah, I mean, I don't know what to make of the image. I'm sorry if I'm ignorant on it.
No, the key part is that
you're drawing.
The flat earthers are right. If the Earth was flat, the horizon would always be rising up to level. But in every case where we actually do measure it, using a theodolite or using, like this HUD where it's showing us level, in every single case where we actually measure keeping the camera perfectly level, the horizon is below level. In all the cases where they say, look at my picture, the horizon is rising up to eye level, there's no measurement. They're just basically pointing the camera to make the horizon in the middle of the camera frame.
Okay, so you're saying it depends on how you point the camera, sure.
Oh, absolutely, but in this case,
the phenomenon to me, I don't know how it translates through a lens. I know that it's that we have two eyes and they're just marvels, that we can actually take in all this data. I found every time I've gone up into a flight, or over a mountain pass or something like that, it's true to me visually. What I see with my two eyes, the horizon goes to eye level. I don't know how that transitions through a camera.
Can I ask you? Can I ask you a question? Yeah. How do you define eye level?
Okay, well, so eye level is wherever the observer, whatever level his eyes are. That's eye level.
Right. So how do you know your eyes are looking straight out in our level?
Oh, that I'm actually looking very. Yeah, I get it. If I perceive it to be level, how can I actually measure that? That's a great point.
Correct. I mean, you can't. Our eyes aren't
intuition.
Measuring devices.
It's intuition.
Yeah.
I thought about this too. The body is actually a scientific instrument, believe it or not. One of my first jobs was doing soil samples out. I was 15 years old. We'd have to go out to the potato farms and you'd push in a core sampler and you'd pull out the earth and you'd touch it and feel it and look at it and kind of gauge what its moisture level was. That was actually using our God's gifts to as an instrument to observe the world around us. So before we can completely discount someone's intuition, that same guy that can shoot a perfect basketball shot from half court, that's pretty amazing that we can do that. So to me, I don't know how to quantify it, and maybe that just makes the matters worse. I understand when you have perspective, something higher up as it moves away, visually appears to get lower. It wants to gravitate to your horizon line that you form with your eyesight. That seems to be true time and time again. So what we have is our senses. People are going out there, and this is exciting to me because I'll start doing some of these tests myself. But I've watched plenty online. People are going out there doing these measurements, using everything they can find about distances of and heights of particular objects, doing these numbers and saying, gosh, the Earth looks flat. And then you bring in the refraction issue, but it really causes a huge conflict, I think.
Yeah. So here's a recommendation next time you're on a flight. And you can get these tools. This is basically a data light app that you can install onto your phone. Make sure you calibrate it on the ground. So find a level surface to calibrate it. But you can essentially see, here's my pitch, here's the roll, so that you can do this yourself. Mm-hmm. That way you're not relying upon anything too often. And I asked this question, like, have you ever tried it yourself? So that next time you're out there, you can wow, now I can actually point my camera with precision. I know what level is, and you can see what the horizon is doing. So I have to say, next time you're flying, do it yourself. Check it out.
Sure.
That's all I ask.
Yeah.
I'm gonna stop mirroring that one. Let's see here. Real quick, your conversation about the video link, which I found is really interesting. Where did it go? Too many windows. This one down here. And this one thing I enjoy about doing this is I learn things. They were talking about this flight, the radio shot from LA out to Honolulu, and they were talking about this trans-Pacific tropoduct. And I was like, what the heck is that thing? And then really, if you go through it and read it, basically talk about, attempts to involve good luck as well as planning. Set a record. Last time it happened, let's see, record was like last June. Only produced good signals for a matter of hours. So yeah, they were able to do it, but only underneath really special atmospheric conditions. It's not something that they could do it and, oh wow, this works every single day.
Let's see, and what did they call that again?
A tropospheric duct. And I had to Google to say, what the heck is that? It's something unique in that area of the world that allows them to send radio signals. And one thing that was different about it is that they weren't using microwave signals, they were using VHF plus signals. I had to go look up, like, what is that? And it's really in the range from 50 to 1300 megahertz, where microwaves are typically in the gigahertz range, which makes them more directional. But yeah, I mean, I'm glad you gave me this, because I was like, what the heck is a tropoduct?
Hey, I'm learning more stuff about this, but when I started getting into this, I had no idea, like how fast the Earth was rotating, how fast it's moving around the sun, what the sun speed is traveling, and all these, astronomically big numbers, for the flat Earth camp just defies your senses. But line of sight transmission, this is really fascinating. There's limits to it because nothing, and people will argue, in addition to light will not go forever. I found a great presentation from the guy at Globebusters talking about the inverse law, and how you double the distance, you half the size, and that also goes for brightness intensity. And so he's that's something way too technical to get into here, but man, he spent an hour going over these physical phenomenon.
Do you think
again, a lot of these things play on intuition of a person, like you and I. A lot of people, I think, feel there's a lot of dogma in science. Theory is theory. It's not true fact. It's they're trying to put all the puzzle pieces as best together as they can.
Do you think light has a distance limitation in a vacuum?
In a vacuum?
Yep.
I do not know.
Yeah,
so I actually
it certainly makes sense in an atmosphere, because there's air, there's humidity, there's dirt particles. But in a vacuum, there's nothing to stop it.
But in the inverse law, it as it emanates out, it reduces intensity, and at some point, it's just going to be.
Oh, I agree with you in an atmosphere, but in a vacuum, I don't think the inverse law applies, because there's nothing to attenuate the light.
I think let's see. The inverse law would apply in a vacuum in outer space. I
I mean,
think
if you can
that
find me anything that shows that, I'd be really happy to hear it. But
here, let's see here. I've got, this is what some of the stuff that I did pick up. One of the things that was interesting too is leveling. That's some pretty intense stuff.
what leveling?
Yeah, leveling, that type of thing here.
Yeah,
In what way?
don't jump around topics too much here.
Yeah,
Sorry.
I'm just kinda
You were
curious.
talking about light.
Where are we? All right, light. Man, I'm getting lost in too much information here. Okay.
Robert, are you done sharing?
Actually, it's kind of setting up for the next topic, but I'll stop for the moment.
Okay. Here, I'm trying to find the slide that I was looking for.
Find it?
Nope, not yet.
Okay.
While you're doing that, give me a second here. Let me
Mhm.
I got a couple super chats, and maybe we can come back to some of these two topics here. Earth is Life says, please mention the QF 14 flight from Argentina to Australia. 9,225 miles, 17 hours, 41 minutes, 517 miles per hour average speed. So I know you're not on that topic anymore, but maybe if you come back around to that. And then Steve6464 says, if the world was flat, then there would not be any problem getting a flat Earth map. A flat map of a flat surface is the easiest type of map to make.
Yeah, I mean, it would seem that way. But allegedly the equidistant azimuthal map is perfectly accurate. Again, until you can go, fully explore Antarctica, if it's fully opened up and people are satisfied there, that's great. Like you mentioned earlier, the equidistant map, it even explained the flight pattern to drop someone off in Anchorage. So it's really accurate in many different ways. So you show me the most accurate map, I'll be happy to use it. The curious thing is, even on the flat Earth projection, you still have, north, you have the concentric circles as they, as it widens, you still have an issue, I think, with giving all the proportions. But again, I'm not a cartographer, so.
That's actually kind of a great segue. Let me know when you see my screen again.
Yep, it's up.
So this is kind of an example. Tropic of Cancer is 24.5 degrees north of the equator. Tropic of Capricorn is about 24.5 degrees south of the equator. On the globe, the circumferences of those are the same distance because they're the same distance north and south of the equator, right?
Okay, yeah.
On the flat Earth, here's Tropic of Cancer, a small circle here. And then Tropic of Capricorn is this much larger one. So on flat Earth, distances for Capricorn would be much greater than for Cancer. And generally, distances south of the equator at the same, 10 degrees south would be much greater than 10 degrees north, right? That makes sense?
I one more time.
So once you get south of the equator,
okay,
as I go further south on the globe, the further south I go, 1 degree of latitude is going to get smaller. Yeah. On flat Earth, 1 degree of latitude is going to get bigger because these circles are getting bigger, right?
Correct.
So here we go back to ForeFlight again. And what I did is I plotted a path. Come on, now cooperate with me. This is 10 degrees north, 0 east to 10 degrees north, 10 east. So I'm just doing 10 degrees of longitude. Here's 0, 0 from basically at the equator to going from 0 east to 10 east. So then here is 10 degrees south, 0 to 10 degrees south. And if we look at the navigation log on this. Remember, I tried to touch it on my computer screen and I can't see it there. So that first leg from 10 degrees north to 10 east is 592 miles. And I got this diagonal line. We can pretty much ignore that. That's this one right here. At the equator, which is, stop it, which is 0, basically right at the equator. I keep trying to touch the screen and not the iPad. That is 1437. So that's the same on the globe versus the flat Earth model. It's exactly the same. But when I scroll up and I look at that final leg, which is this one down here, which is now 10 degrees closed, darn you, which is 10 degrees south. Instead of it getting larger, it's back being that same 592 nautical miles as it was north of the equator. Or it should be bigger if the Earth is flat.
Yeah, I mean, according to this, you're right. I haven't been there. A fun one for me was when someone said, hey, you take a globe. Yeah, you know the Earth is a globe because if you walk 10,000 miles in one direction, take a 90-degree turn, 10,000 miles that direction, another 90-degree turn, you actually start at your point, you make a square. And I'm like, wow, that's really cool. Let's go try it.
I had applied that once, but I think I deleted it, but it actually makes a triangle. And it's something you couldn't create that. So it's basically only, boom, boom, boom.
You'd have to be on a sphere to do that. And I'm like, man, that's super cool. But I mean, how do we actually do that proof, And it seemed like, the flat earthers.
I could do it on a very, very small scale. Like I could literally say, make a 50 miles, 50 miles, 50 miles. I can actually go fly that in the real airplane.
Yeah.
I should do that one day and then come back and show the ground track. I'll have to do that someday. I think that'd be kind of a cool experiment to show it. Now the problem is that you'd have to go up on a day when there's no wind.
Yeah.
Because the wind's really going to mess with us. But
yeah. What about the Coriolis effect? You didn't mention that yet.
It has such a minuscule. We could go off on a tangent for hours on that one. But
before
for a powered aircraft, if I'm navigating along, that is such a tiny effect that I'm not even going to notice it.
Yeah, well, I love Neil deGrasse Tyson. It was a football game. He mentioned that someone kicked a field goal, and he's like, it was a north to south field, and he said, well, in the rotation, the Earth deflected the ball about a third of an inch, and that's definitely ball.
Yeah.
Big proof. Hey, I've got the inverse stuff we were talking about.
Sure. Let me stop sharing. You can show us what you got.
All right, so basically, I don't think it matters if you're in a vacuum or not. As light emanates from a source, when you double the distance, you reduce the intensity by half, and at some point, it's just a vanishing object. It doesn't matter how bright it is. So when you take the sun at its luminosity, and you can calculate how bright is Mars going to be, or Jupiter, which is even further, and you start applying this, like I mentioned, I won't steal from Globebusters too much, but they're really, really compelling points. Light does not travel an infinite distance. It can't. So that's the one thing. But here's.
Can I ask something there?
Yeah.
Yeah.
Did Globebusters do the math?
Okay, so you can check the math. I can put the link in the video afterwards.
No, did they actually do the math, or did they just say, if you do the math, this is what would happen? Did they actually do the math?
He put the numbers up, and I mean, as much as anybody would do, right? One way or the other. So I mean, it was an hour, 15-minute presentation, strictly dealing with this topic.
Okay, who was the presenter?
Bob Nodell.
Oh, it was Bob himself that did it. Okay.
Yeah. So I
Bob,
mean, and I mean, it's not just me that is willing to have these conversations. This is something that strikes me. The Feynman, there's numerous mathematical formalisms that describe the same physics. The packaging is different, but they're equal as physical theories. They always give the same measurable results. So he liked the idea that a theoretical physicist should familiarize themselves with 6 or 7 formalisms for the same physical phenomena. And so for me, that really opened up the idea that, I have permission to to look outside the normal view.
Yeah.
In fact, if people didn't do that, we would never have revolution in science.
Yeah. I mean, it would be interesting to see the math, but one funny comment about Bob Nobel. Bob, a couple of years back, claimed to be a commercial pilot because he was basically trying to use that as it's Earth is flat. I'm a commercial pilot. But the problem is that every American pilot shows up in the FAA pilot database, which is public. You can public access. So of course, first thing we did, we went and looked at it. And lo and behold, he's only a private pilot like me, wasn't even instrument rated, and he hadn't flown in about 20 years. So he's got a record of not exactly being the most honest guy out there, but I'm not going to dig in much more than that.
I went to the Flat Earth Global Convention in Dallas in 2019, and I brought with me both because this was discovered on the 2018 Flat Earth Global Convention website, where he made the claim that he was a multi-engine certified pilot, and then got caught, and the website was changed, but the Internet Wayback Machine still has the original, where he says the multi-engine certified. I brought both printouts with. I was going to have him sign it, but I never got time to have him sign the multi-engine certified claim.
Yeah.
Maybe him and Biden went to school together.
What's your thought on the firmament or the dome?
I mean, again, so much of this is shrouded in mystery, right? So you wake up. I believe in the globe, and there's crazy people telling you, no, look at this, and you start looking at this, and there's just so many anomalies. For one, Antarctica is restricted. For two, you have Admiral Byrd sailing to Antarctica with 4,500 troops, and you have Operation, what was it, High Jump, which was to get over the ice wall. They called it High Jump. You have Operation Fishbowl, where they were shooting nuclear devices up in the high altitude, allegedly, shooting the dome. Honestly, I don't know. I mean, there's a lot of mystery.
I'm curious. You're the U.S. military. You're firing nukes up. Flat Earthers claim that they're trying to break through the dome. Don't you think that would be a bit self-defeating? You're trying to break the dome, which keeps the waters above. They would be trying to destroy us. Does that really make a lot of sense?
I don't know. I mean, does
I don't think they would be purposely trying to kill us.
Does my lizard in the terrarium have any idea what's waiting for him outside? I mean, he might just think it's more of the same. But,
it doesn't make a whole lot of sense that they would be trying to kill us. In reality, they were doing high altitude nuclear tests to test the result of the EMP pulse. Because instead of going in there and directly nuking Russia, you fire or you explode some nukes over Russia and destroy all their electronics. That's what they were testing. They weren't trying to break the dome.
That's great. I think there was Operation Dominic with it too, which is so they're trying to say, they're talking about Fishbowl of the Lord, because if you break down Dominic, the code name it means there. But I mean, again, it's same thing. I have friends that like to talk about the hollow Earth. That's an interesting theory. You've got convex, concave. It's all it sounds absurd. The reason why the flat Earth one keeps creeping up is because you can get your P1000 camera, you can go out to the coast, you can say, hey, I know this oil rig's supposed to be this far away, and zoom in on it and punch that into the curve calculator and say this doesn't make sense. So you have that. Now I understand the answer to that is using refraction, but that can't be the answer for everything.
I got a great one to show you on that, but I wanted to ask you a quick question to kind of stick the dome. So theoretically, if there was a dome, and as they say, the dome holds the atmosphere in, right?
It would be a container, I suppose, and
enclosed. All right. So that
is the idea. Yep.
Are you familiar with the pressure gradient in the atmosphere?
Yes. Well, I mean, if you can ask me to tell you the exact number of it.
No, I don't need that. I mean, I'm going to share out my screen again real fast here. I can't wait for it to come up on the main screen. So this graphic is just, you go from, 0 kilometers, this is in millibars, and as you climb higher and higher up, the air gets thinner and thinner and thinner. I don't know if we're seeing. Okay, oh darn it, my YouTube keeps going backwards. Okay,
Yeah, we see it.
so the higher you go, the thinner the air gets, and it's very, very irregular. In fact, that's how the altimeters work in the aircraft. Is they're actually measuring that reduction in air pressure. So that's what tells us how high above the ground we are. And before we take off, one of the very first things to do is they call it the Colesman window, but there's a little adjustment on the attitude indicator that you adjust for what the current pressure is at your departure airport. And as you're flying along, you'll get weather reports from ATC saying, okay, local pressure is now, 3002 or 2997. And you adjust that little Colesman window so that your altimeter is accurate. So the higher you go, the lower the air pressure gets. And one of the cool ways of looking at that, this is I bought a weather station, which is I'll just kind of show you what it looks like. But I added one of these to my house, and it kind of got me thinking about this the other day. Is that you can actually look at, there's thousands of these things around the world. So I looked at their map, and this happens to be the mountains of Colorado. And I actually can come in here and I'd say, show me the weather in Leadville. So right now in Leadville, the station pressure is 20.958 inches of mercury. If I come out to the western slope of Colorado, over near Glenwood Springs, I'm trying to find Grand Junction here. There it is. Here's Grand Junction. So Leadville's at around 10,000 feet. Grand Junction's only at less than 5,000 feet. What do you think is going to happen when I look at Grand Junction? Have any idea? If I'm at 20.9 here at 10,000 feet, what am I going to see in Grand Junction?
All right, so Grand Junction,
a little less than 5,000 feet, half the altitude.
Half the altitude, and what's the pressure?
Here in the 10,000 feet, it's 20.9. What do you think it's going to be in Grand Junction?
Well, light refracts to the denser air.
Now, this is not talking about light anymore. This is purely just air pressure. That's it.
Oh, I mean, enlighten me.
Okay, well, we're going from 20.9. And when I look at Grand Junction, let me pick one that's not doing millibars. Come on, people, do it inches. There you go. 25.5. So 5 more inches of pressure at Grand Junction versus up in the mountains at twice the altitude. So they always say that air pressure will always equalize from the high pressure to the low pressure. Mm-hmm. Why isn't this air pressure equalizing? This is only maybe 100 miles, not even that. Why isn't that air pressure from Grand Junction equalizing up to that lower pressure at the top of up in Leadville?
That's a great question. I actually live in Washington on the southeast corner of the state, and what's really interesting is all the water drops on the west side of the Cascades. So what happens is we get the warm air that pushes down, but then we also live in a fishbowl. So even if there's a little weather that's coming, it might just blow around us. It might swirl around till it falls in. Mm-hmm. I don't know how all those things interact, but these are all really great things. I mean, this is why I love this. This is something I'll be even looking at further. You asked about the dome, and here's if I could share the screen.
Yeah,
and I might talk about this. It actually is related, I think. Because we're trying to find formalizations, ways to understand the same phenomenon in different in a different way. So, are you familiar with dielectric acceleration?
A little bit. What was Nathan Thompson's term? Oh God, what was that, Mike?
The electromagnetic wake.
Yeah, electromagnetic wake. Are you familiar with that?
No, that's different than dielectric. Whatever.
Well, there's dielectric acceleration, incoherent dielectric acceleration. Basically, the idea is we're surrounded by electricity. We can measure it, we can generate it, we can actually pull it out of the air, all of that stuff.
Okay.
And so, the gravitational theory is the theory of gravitation is a description of the long-range force that electrically, neutral bodies exert on one another because of their, matter content, right? Yeah. That's one way to look at it. Here's this guy. If you only know the name, you know nothing. So we don't know really what gravity is. We know what its observed effects are.
Yeah, agreed.
So we talk about electricity, and so the ground has a negative charge, and as you move up further, according to this theory, you have a higher kind of electrostatic charge to the air. So you wind up with a constant electrical field. So if you have a Gaussian plate where the Earth is the floor and maybe the dome is positively charged, you would have a natural occurrence of this electric force that moves downward. So if you didn't have a field, the molecules could arrange themselves like however, like if you had a magnet and instead of having a definite north or south node, you just mix it all together, and that is what would happen without the Gaussian plates. But when you add the Gaussian plates, they arrange themselves,
Do you think
and
we
then
would
you
be
have
able
a
to
positive negative.
measure this field? This is an
Well,
electrical field.
so we have the ionosphere. In this example, you have the negative charge as you move up.
Yeah.
It'll also explain, like in this example, if you could imagine hydrostatic water, the water's moving down through a grate at a constant rate. That's kind of what's happening. This electric charge is transferring, energy down. Let's move forward. So when you reverse the electric fields here on Earth, what you find is that you can make wood, iron, hair defy gravity. You get you change electrostatic charge and you're defying gravity. In this example, they're making water bend by putting a charge in the sphere over it. So it's really fascinating. He even goes on to show that as you get heavier molecules, their the potential becomes more, so they're more attracted, and that's why like lighter um, elements will be higher up. In this example, he ties something to a balloon, and he's able to change the weight. It shows it going up and down by changing the charge
Sure.
on what's hanging off of it. So they talk about polar gas by external, this type of stuff. When you have gas in the atmosphere and you have it ionized, we get beautiful sunsets. Hydrogen, helium, nitrogen, oxygen, it'll arrange itself like this due to its electric nature. So it describes everything perfectly. Pressure, density, gradient, all of that stuff that you mentioned, it's there. This is an example of, making hair weightless. That's great.
Yeah.
This is an interesting example because it shows how it's creating this electricity, the static arc, which looks kind of like lightning storms, doesn't it?
Yeah.
And so we have a whole complex system like this, and it's an electric it's an electric universe, really.
Yeah.
So
I would think if it was electric or static kind of causing, it sounds like you're trying to say the atmosphere is being pulled down because of static versus mass mass attracting mass.
Right, because the ground has an electric charge.
Yeah.
Whatever is up, maybe it's the Van Allen radiation belts. Hey, there's a highly charged band of particles that at least both of us can agree on that's up there. So that would have this effect.
Yeah.
So there's a lot of experiments, and I can't remember the names that you can Google but getting levitating objects.
Go ahead, Mike.
Yeah. So I have a background in electrical engineering. So if it's about electrostatics, then it's about Coulomb's law. Coulomb's law is about the big thing about Coulomb's law is the distance. It's very similar to the gravitational equation, right? It's a constant times the charge of the one object times the charge of the other object divided by the distance between them. And it's the distance of the surfaces between them, not the distance of the centers of them, right? So if this is your object that you're connected to, it's not the center of it, it's the edge of it. So it's the distance from the surface of the Earth. If what you were talking about there, the distance of the surface of the Earth. So if you're 1 meter above the surface of the Earth and you double that to 2 meters, it's the inverse square law again. You don't slightly reduce the gravity in this model. You divide by 4.
Gotcha. Well, so in this
we
example,
don't see that.
Well, in this example, you're between two Gaussian plates. It's not just a single source emanation. You have positive, negative, and a flow is what he's describing. So that's the dielectric acceleration.
Yeah,
so
again, that's none of that is actually would work. Also, you can in a Faraday cage, you can neutralize all of that, and So any electromagnetic interference inside of a Faraday cage is neutralized. If it's electromagnetism or anything related to that, then inside of a Faraday cage you would float. If it's electrical charge, then if you just connect a wire to the ground and a wire to the object, then they're at the same electrical potential. And again, it will just float. There would be no downward force.
So are you familiar with the theory of dielectric acceleration?
It's not a theory. It's not even a hypothesis because it's not really testable. It's just a vague idea.
Okay, kind of like gravity?
No, gravity is empirically confirmed many, many times.
I have never came across a gravitron.
You don't know that's not the empirical evidence for it.
Right.
The empirical evidence would be testing to see whether or not things with mass attract each other. That's been done and confirmed many, many times.
So how did they test that? Because as I understand it, like one possible test is you take a steely, top of a wall that has a huge mass, and if you drop that steely in a vacuum chamber, even, will it come closer to that wall?
What's a steely?
Or like a steel ball, steel marble.
Oh, that's not the test that I was referring to.
Okay, or if I put a huge massive weight and take really tiny objects and set it around it. I mean, what is this test?
Yeah, it's a torsion.
These are the things I need to know.
Yeah, it's a torsion bar. So you have a bar, right?
Mm-hmm.
And you suspend it from a wire, and you have that the wire needs to be strong enough to hold it up, but allow it to twist, right? And you have a mass on either side of it, and you let it come to rest with nothing near it. Then you introduce a large mass on either side of it. And if mass attracts mass, then that will rotate towards the masses. And you can actually, knowing that the torsion constant of the wire, you can measure based on the distance that it moves the force that's applied to it. There's other ways to do it, like the time it'll oscillate, and you can use the oscillation time to measure that force as well.
Okay, I'll have to check that because as I'm trying to debunk flat Earth claims, the ones that are the hardest are the ones that are hardest to test. So like everything that I've heard is and read is they haven't actually ever proven or seen mass attract mass. Like at what point, that supposedly only works on the large scale, like when you get into celestial bodies in outer space.
So I can send you, I have 18 scientific publications on that topic.
Okay.
But here's what's not been proven. Incoherent dielectric magnet, whatever right? That is, like I said, just a vague idea with zero empirical evidence supporting it. So if you're going to go down the road of dismissing the things that don't have backing evidence, that one is the first in line.
Well, I don't think I said I was going to just dismiss anything. I mean, when someone offers up a claim, I like to look and search it out. Certain things like this, like the ISS, people getting photos of that in front of the sun and the moon. I mean, that really defies, any kind of logic that, if the Earth is flat, how does that work? And until you, like we, talked about with the Feynman quote.
Well, I do want to talk about that a little bit, but I wanted to show you real quick so we get stuck on one topic. We've only got about 40 minutes left.
There's a lot I wanted to cover too.
This is a couple more experiments you could do on your own. This is every smartphone today has a pretty accurate barometer in it. So right now it's sitting on my desk, but I'm going to drop my phone on the floor. And sitting on the floor, the pressure in my room is 24.496497 inches of mercury. That's on my floor. I've got the fan, if you notice above my head, I've got the fan running because I've heard others are saying it's like, well, your layers of different air are you know, got hydrogen up here and your thicker airs down here. Well, I got the fan running on high behind me, so the air in the room is all mixed up. Just kind of eliminate that. So I've got on the floor 24,497. I'm not going to raise my phone. I have to hit my hand on the fan. 24,492. So just from my feet on the floor, 24,491, to the top of the ceiling, the pressure dropped, even though I've got the fan running on the room. Something you can test yourself. Go outside, you know, drive down a hill, measure it, drive up a hill, measure it, and then ask yourself, why isn't that pressure equalizing from low to high? I got one other one for you. Talk about gravity. This is an accelerometer. Another thing you can install onto your phone. I got the phone is just sitting flat on my desk. I'm going to help start measuring. You'll notice on the z-axis, this is basically measuring G. So G forces is right about 1 G on the z-axis. So that's going down through the back of the phone. I'm going to now set the phone on the left side. I'm trying to bump it too much. So now that 1 G has moved to the x-axis down through the left side of the phone. Now I'm going to stand the phone upright on its tail, and you see that 1 G of acceleration is now moved to the y-axis. This is something you can do yourself. And no matter, you know, if you kind of get in a weird angles, you'll kind of see it proportionally. This is something you can absolutely do yourself. What do you think the phone is measuring?
What do I think the phone is measuring?
Yeah, what's your guess?
I mean, you can tell me. I mean, no one's going to argue that gravity can be observed, you know, 9.8 meters per second squared. It's, you know, acceleration can be measured. There's, I mean, a lot we can fundamentally understand about gravity. So whatever mechanism they're using, I know they have, you know, phones can know what orientation they're at, you know, I don't see how that'd be really difficult. My question is, what would happen if you go up to Mount, you know, Everest? Would you be able to determine any fluctions in gravity, or is it always reading the same? I mean, is this a tool we could use to find anomalies in the gravitational field, or is it just a program that aligns where the center of gravity is going to be with the x and y axis of the phone? I mean,
and you do make a great point. I mean, we know that if you're at the equator versus, you know, you got 1 ounce of gold at the equator versus 1 ounce of gold at the North or South Pole, that at the equator, it's going to be fractionally less weight. And that's from the centrifugal force of the Earth rotating. Now, is it a lot? No, it's very, very tiny. But they actually, you got like a diamond or a gold market, they have to compensate. They take the same scale from one place to the other so that it gets the exact same measure. Because if they just said, I'm going to go use a scale calibrated at the equator, then they may be getting cheated on, you know, a couple of ounces of gold on a bar of gold.
Hey, speaking of which, wouldn't that be great if you could use a device like that and find huge amounts of gold under the ground, because
it would
more mass, maybe more gravity. I don't know.
do that.
But the point is that to kind of close out the whole dome conversation is when they say that the dome has got to hold the atmosphere in, you can have pressure against the vacuum. Well, you know, at no point, if you kind of go back and look at where did it go? Oh, tell me I closed it. Darn it. There is no point that you would have high pressure sitting next to a vacuum, because the pressure gets lower and lower and lower and lower as you go up until you eventually reach a vacuum. It's not like we've got 14.7 pounds of pressure that we have at sea level sitting right next to some vacuum. It just gradually goes up, and whether we call it gravity or we call it your electromagnetism, whatever force is pushing down on the atmosphere is that same force that would keep it from escaping out into a vacuum. So there's no need to have some container holding the air in. It's like whatever downward force you want to call it by whatever means, that's what's keeping the atmosphere here.
You're right. So you say gravity alone keeps the atmosphere here.
Yes.
Okay.
And we do lose. I mean, we do lose. I forget how many tons of hydrogen they say we lose there every year. We lose a little bit, but it's a like tiny fraction of those super light. That's why I'm sure you've probably heard is like, there's an atmosphere around the moon. Well, it means that they
Technically, they
use
say that,
hypersensitive instruments to realize there's like 1 atom of hydrogen per cubic meter of
yeah,
space. I mean,
technically the
yeah,
moon's still in Earth's atmosphere,
it
a
was
portion
stupid.
of it.
Yeah. Because
So, but it's really interesting because, you want to find these hard answers. Okay, so where is the edge of space? There's no consensus on where the edge of
there's
space
no
is.
defined edge of space because it's a gradient.
Sure. So you have a gradient, right? Nowhere else, so from the everyday perspective,
Yeah.
there's no instance where you can have a vacuum juxtaposed next to a non-vacuum without a barrier, right?
When you're talking about, I've got my soda can sitting on my desk. That's, I think soda cans are like 30 psi compared right to the air right next to it. Sure, because you've got a large differential between the pressure in the container versus on the outside. But we don't have that in our atmosphere. At no point do you have a large differential from here to here. It gradually gets lower and lower and lower over thousands and thousands of miles until you eventually reach a vacuum. So the analogy of I can't have this pressurized cylinder right next to non-pressure and they won't equalize, it's a fallacy because it's not a gradient.
Yeah, and I mean, I'm looking into that argument too. I was actually just looking at that yesterday.
Yeah.
What's odd is you would say, okay, so then gravity is enough to pull everything to the Earth. Now, does it hold everything rigid as it orbits, right? So, what I'd like to see is somebody in the space station, take a camera and focus in on somebody, in Australia flying west. I'd love to see that, how fast his relative speed would look and all of that. That would be, man, that would just, I'd sign the check right there. I'm done.
Yeah, and you can find some footage of that where the camera, they basically just fix the camera down, and so you're seeing the clouds moving by pretty fast. But a lot of times they're, oh look, Australia, and they're focusing as they go by.
Yeah.
But if you look, you will find fixed camera footage where the camera is just facing down, and it's moving pretty quick.
Yeah, so what's curious now is we talk about Coriolis effect. So they say, well, there's a Coriolis effect, but snipers don't need it, to worry about. No one actually uses it in any calculations.
Snipers
allegedly.
Do. Snipers do.
I work with it. He's a sniper. I talked to another sniper. They said we'd never actually calculate that in. I know they talk about it in the field book or whatever.
There's some that do.
Yeah. So
again, you found a couple that don't, but there's some that do.
Yeah. So my question is, if you can fire a bullet, and you do need to worry about the Coriolis effect, right? Because the bullet now has a separate motion than the Earth, and so the Earth will rotate underneath it. What makes that any different from, say, taking a helicopter and hovering 1,000 feet over New York and waiting a few hours as the Earth rotates underneath you?
That's not Coriolis.
Land in Paris.
No, it's not.
Okay, so
yeah. All right, so let's define why don't you define what you think Coriolis is and how it would affect things?
Okay, so and I know you're going to have a great understanding because you're a pilot, right? Yeah. So
actually no, because in pilot training we don't talk about Coriolis because it has such a minimal impact on the aircraft. But I want to know what your understanding is of it.
I took a couple private lessons, and the guy really loved talking about the Coriolis effect.
I don't know why, but okay.
But it's well, I mean, it's got to be there.
Yeah.
So it's supposed to be there. So I mean, we should be talking about it more and measuring it, because that's a great feather in the cap of the globe. But as I understand it, let's use Neil deGrasse Tyson for instance. He said when that ball was kicked, by the time it went through the uprights, the rotation of the Earth underneath it deflected the ball 1/3 of an inch.
Yeah.
I don't know which perspective you'd like to look at it from, but I suppose the idea is the Earth rotates, and gravity's not so static and so strong that it's a rigid thing that's moving along with this rotation. So that's why a lot of cognitive dissonance happens in the flat Earth camp. Well, hey, if how come you're not worried about which angle the runway is at, or how come you just don't go reverse the direction of the spin and all these things? And
let's talk about it for just a moment. I gotta share my screen out again. You know, it's you know, I know you love Neil. You know, a
And you don't.
third of an
50.
inch, um, third of an inch over the length of the football field, or 50 yards, whatever it happened to be.
Yeah.
How much would that be over a mile? Maybe a couple of inches, maybe even a foot. So if I'm flying,
you're showing the video screen. We're getting
oops, sorry,
picture in picture. It's awesome.
I
That's
shared the wrong one. Share again. There we go. So, you know, even over say the length of a mile of me flying due south or due north, you might be talking about 1 foot of Coriolis effect after flying, you know, over 5,000 feet. So it's a very, very, very tiny percentage.
Okay.
And the wind is actually having even say a 5-knot wind is going to have a much more drastic effect on my flight path than that 1 foot over a mile of travel.
Okay.
So if I got a 5-knot wind and I'm flying 120 knots, that's now, I gotta get to the math in my head. It's put me, you know, dozens, if not 100 feet off course versus having that little bit of Coriolis. And it's a little bit different now because now we're using GPS, and GPS is basically keeping us right on course, and the aircraft will automatically make a wind correction. But even without that, Coriolis is such a minuscule difference compared to what wind is doing to us that we don't even factor it in.
Right. Okay.
And you see that where, I mean, you're going. Sorry, what the graphics showing is you're going from 1,000 miles an hour at the equator, but you've got to go. Oh God, help me with the math, but 6,000 miles to get up to the pole. So 6,000 miles for you to slowly slow down from 1,000 down to 0. So it's an extremely gradual change. It's not like, wow, I traveled 100 miles, I've gone from 1,000 to 0. It's so incredibly gradual that we're not going to notice
it. Okay. So you're saying, let's say you're at the 963 mile per hour and you fly south.
Yeah. So that's
it won't have a great effect to you. So that's like 40.
No, the wind is going to have a multitude more effect on me than the Coriolis. Let's talk about your helicopter first.
That's really interesting. I know, and no, this is fine. I mean, that the Coriolis effect is so minimal. I mean, we don't have to talk about the helicopter if So the Earth is going to be spinning maybe around New York at 792 miles an hour.
I think it's worth talking about the helicopter.
Effect is.
Yeah, I love talking about the helicopter one. But you're right. So the Coriolis is, I'm at the equator and I fire a bullet southbound. So that bullet is your gun standing on the Earth. You're moving along at 1,000 miles an hour. You fire that bullet due south or due north. As the bullet is now airborne, being unguided, it's not being you can't steer it. It's an unguided projectile. It was fired at 1,000 miles per hour. It's going to keep going at that speed. But the surface of the Earth underneath it is slowing down as you go further north or south. So the bullet is traveling laterally faster than the Earth itself. That's Coriolis.
Right. And you just said that's something you don't actually take in.
No, because it's so tiny for an aircraft perspective. Like I said, the wind has much more an effect than Coriolis ever would.
What's fascinating is as far as just
when you're done with that.
Yeah. And this was just another point too, because just like I know you probably bumped into the guy that I mentioned, the master gunner, celestial navigation. So he says the military also just gets rid of refraction when they're doing celestial navigating. They don't even worry about refraction. They're just actually looking at the straight object, which is interesting because if you're looking at something in a celestial sphere, you would be passing through more atmosphere that, it's just curious when you want to omit these factors or include them, especially, you'll always include refraction on ground level to make sure that the curvature measurement comes out right. But I haven't had a chance to share some of these slides. I'm sure you've seen them. I'm sure anyone tuning in could find them, but just a lot of optical evidence, pictures, where you're getting this flat plane perspective. So again, it's crazy that it's a growing movement. Maybe it's just we're
Yeah.
getting dumber as we're getting more information. You tell
I
me.
don't know. I think. Yeah. So let's talk about your helicopter for a second. So I got a helicopter. I'm at the equator. I'm sitting on the ground. Helicopter, me, Earth, all moving along 1,000 miles an hour on the atmosphere at that area, except for winds. Everything's moving in the same plane of reference, right?
Mm-hmm.
So I take off. I hover 10 feet above the ground. I'm still sitting in the atmosphere. Atmosphere that's holding me up. The atmosphere is still moving along. I'm saying zero wind. Ignore wind at the moment because wind's usually a factor, but no wind. The ground, helicopter, the atmosphere are all moving 1,000 miles per hour. So why would the helicopter, as soon as you lift off the ground, all of a sudden start doing this?
Yeah, it's curious because when you get higher altitude too. So wasn't it about 40,000 feet?
Yeah, but ignore that. Ignore that for the moment because
Yeah.
you go to higher altitude, you get jet streams, all that kind of fun stuff. I want to ignore wind. It's just that you always hear, hey, if the Earth was a globe, a helicopter takes off, it should just be able to hover there and watch the Earth catch up to it.
Right. So
But
you're
if
saying
the ground, the helicopter, and the atmosphere are all moving in the same frame of reference, that wouldn't happen.
Sure. So like you said, if the frame of reference is it's rotating at 792 miles an hour, the helicopter lifts up, it'll start losing ground if it's just hovering, right? Can we measure that?
Why? What would it lose?
Well, like you mentioned, if you're flying,
Yep.
it's like what, a foot or some minimum distance.
10 feet above the ground. Sure.
Okay. So how can we measure the Coriolis effect? I mean, is there a test? Can we set it up in a vacuum chamber, hover a balloon or something like that? I mean,
Coriolis has no impact on the helicopter because he's not moving north or south. He's hovering. He's stationary over the ground. So Coriolis would have no effect.
I need to jump in. I think we have some questions from the audience if you don't mind.
Sure.
But you want to stop sharing your screen there. The thing about Coriolis, Brad, is it is directly proportional to the velocity of the object in relation to the surface of the Earth. So if a helicopter is hovering, the velocity is 0. Being directly proportional to that velocity, you just multiply it by 0, so you get 0 Coriolis.
Okay.
And so I hear that misinterpretation, the misunderstanding of Coriolis often, that you could hover a helicopter. But conservation of momentum is taught to, we teach it in elementary school, and that's why a helicopter wouldn't just take off and then the Earth would spin underneath it. So
Yeah.
Okay.
All right, we got 20 minutes left. That's if you want to ask the audience questions, but I want to spend like the last 10 minutes just asking some fun stuff.
Yeah. Okay. Well, I have another one after this, so I can't go directly up to it. We can, because this has been a good conversation. We can do.
I mean, I haven't really gotten to the optical and the home.
I don't think we're going to get to that today.
Yeah. Yeah. So maybe we can do this again.
Yeah. So, all right. Lael, King of the Flurfs. He's not actually Flurf. He says, correct me if I'm wrong, Admiral Byrd was part of government Navy. Bradley, why do you trust him if the government is lying to us about the shape of the Earth?
Oh, gosh. Who knows, right? It's really interesting. With NASA, you have Operation Paperclip. You have virtual Nazi war criminals, scientists that are heading up this operation. Your guess is as good as mine. I mean, you have Operation Mockingbird, where they're infiltrating news media with CIA. You have a lot of narrative that's being, controlled by our government. It is what it is. So I don't really know how to answer that, to your satisfaction, but.
Okay. All right. Harry7 says the people influencing you, I think that's Globebusters and other similars, have been proven to be liars. Verify the integrity of your sources before parroting the information.
Okay, so I came in with trying to use as much factual data from, commonly accepted sources. Obviously you got Neil deGrasse Tyson up there. You guys threw him out right off the bat. I brought more, but I don't have time to get to that with you. But this is not a debate someone's going to just win. I mean, that's actually one of the discussions I want to get into, is the whole philosophical argument behind this. Fundamentally, why somebody would reject what the dogmatic, institutions are putting on people, and maybe they're just your do-gooder institutions that are, just trying to teach the world everything. I don't know. I mean, theory is theory. Fact is fact. So I look at it from the ground level. I'm taking a camera out to do a test. I'd love to do some tests with you if you can devise some, because I like the globe. I like outer space. I like all that stuff. Sidereal
One thing that would
days.
be pretty cool, since you live in that Seattle area, is you've got so many ships that are going out to sea, go out, make observations in different atmospheric conditions. I forget the island, but you know where the Ferris wheel is?
Yeah.
Yeah, so go to the island, like across the waterway from that, different atmospheric conditions, zoom in with that P1000, try to figure out why is the bottom of that Ferris wheel missing.
Mm-hmm.
So yeah, I mean, it's great you get in the camera, go out there and make your own observations. That's something I keep saying over and over again. It's like, don't trust the globebusters of the world. Don't trust me. Go out there, run these tests yourself, and then draw your conclusions from it. Because too often, I mean, you've said it, you've watched a lot of videos from globebusters and people like that. We see that in your statements. Ignore them and go out there, do your own tests.
Mm-hmm.
I've done quite a few myself, because obviously there's agendas on both sides.
Yeah. Hey, I'm happy to confirm the globe. I'm happy to confirm, I don't have an emotional stake in this, but it's a much more interesting topic that's got me to look into our reality a whole lot more on a scientific level as well, and talk with great people like you. So I feel like Mike's getting ready to get ready.
But yeah, I know Mike's wants to finish the super test. I got one more thing. Actually, two more things I want to show you real quick. But
I have another question from MB Stevens, who says, Brad Pilot here. Why do I need to climb to 4,200 AGL overhead my home airport before I can talk to the airport 78 nautical miles across Lake Huron?
Towers have limitations. I don't know. You had ground positioning radar. You've got ways to transfer data and everything through microwaves, radio frequencies, and it's all on the ground. I mean, how much of this stuff is actually coming from satellites? I don't know.
None of the airport 78 nautical miles across Lake Huron is coming from a satellite. Nobody claims that, right?
Yeah, I mean, throw it in there. I'll look at it. And again, there's a lot of things that are not issues for the globe. I mean, the globe is the predominant viewpoint. The flat earthers are the ones that they've got a lot to show. I remember the first time I learned about the sidereal days. That's interesting. An actual day is 23 hours. Yeah, 23 hours, 56 minutes, an actual day. So you learn more of these layers. If he wants to put that in the comments, I'll go back and look at it too.
All right. William Foley, this was the dielectric, or the incoherent dielectric acceleration, said AB Science just developed a headache for some reason. AB Science has addressed Ken Wheeler's nonsense a few times. And the dielectric, the incoherent whatever garbage is from Ken Wheeler, who does not think the earth is flat and is very upset that the flat earthers are using his nonsense. He'd rather have his nonsense be his own nonsense.
Yeah.
All right. Corntech says, why are cirrus clouds in the east illuminated after sunset for a while longer, but lower level clouds are not, let alone the ground?
Oh gosh, P-Brain, you can Google him. He's got a lot of good stuff on it. And I'd recommend anyone to use DuckDuckGo as a search engine. So those questions you posed to me, I think you'll find enough content online to keep you busy for a Friday night.
Yeah, I did. It was nonsense. Okay. Mute Decibel says, flat earth is a verb, as in to keep from accepting any facts. Gary kept flat earthing from one subject to the next.
Okay,
Gary's a guy in the chat.
let's
So
let's go like this a little bit. I get it. There's a whole lot going on, and people are just thinking that anyone who thinks the Earth is potentially anything other than the globe has got to be crazy, right? So just to close out, if we didn't have proofs like these, where they're showing mountain peaks, distances, elevations, where you're seeing beyond the globe, flat horizons, horizontal, skylines, you still are going to have obstruction of some of the lower, just because of how our eyes create a horizon line. Sea level, you've got the canal here. I mean, 1946 picture from Earth. You've got the Kotoa Islands. I mean, it's not just me getting up here and being all like, hey guys, Earth's flat. It's like, literally, this is what's going to happen when you get online and you're not on Google and you punch this stuff in. Some of it's crap, some of it's not. We live in the information era. It is not filtered. The less filtered, the better, but you'll have to use your brain to figure it out. And also not be afraid to discuss it in front of 300 people and take the view of the devil's advocate for the globe. I mean, it's how we learn, but we have examples time and time again. Also, you can type in there pilots who say the Earth is flat. There's pilots who say they're not. So people are getting up in a plane having two different experiences with what they think they're seeing.
So here's one thing I challenge you there on, Brad. Mm-hmm. Find a pilot who says the Earth is flat, who will actually validate their credentials. I challenge you.
Well, you
could do better than that, because the answer is going to be, and I know what you want to say.
Yeah.
They would get fired. Fine.
Yeah.
Plot out the flight from Santiago to Sydney, and they can be anonymous. Just send that flight route. If they're an airline pilot, they can plot that route. Just send that plot on Flat Earth charts.
Yeah. Not to mention the tens of thousands of retired pilots who don't care about getting fired because they're retired. So.
Right. I mean, you said they have to back it up. I mean, so if I were just to ask a pilot, say, hey, do you think there's flat around? And he says flat, now I have to make him, do homework. So maybe that's why.
Well, and generally when you've seen the few videos where they Shanghai the pilot, hey, is it flat? Yeah, it's flat. Yeah, trust me, they're basically pulling their leg. That's one of the biggest jokes.
This is not a popular position. I can understand why people don't want to get up and sit on this side of the debate. I don't really care. I'm not here to insult anyone's intelligence. I'm actually working through the problem. I didn't go to college to get a physics degree. This is the next best I got talking about you.
So real quick, Mike, you got any more super chats?
Two more. One is not a question. It's from Corn Tech again. Says, Brad, get an FM scanner with a Jaggi antenna to hear the NA1SS using a ISS tracker, while also witness Doppler while tuning amsat.org/amateur-radio-on-the-ISS. So I will put that. It's hard.
Put that in there. Hey, and I'd love to if anybody wants to work with me to get a picture of the ISS.
Jaron did it.
I'm pretty sure. I'm not Jaron.
Yeah.
So if anyone in the comments maybe lives in Southeast Washington that knows a thing or two about how to get that shot.
Well, I'll finish your last one, Mike, and then I'll kind of finish up with that.
I have one more. Then what I'm going to do is I'm going to go to the bathroom, and I'll let you. You're
right.
You can't change your sharing status of the screen while I'm not in the room, because it'll get all messed up.
I'll just share. But
okay, Sir Little Wolf says, why does Barrow, Alaska go 2 months without the sun during winter?
Go it. I didn't come here to actually be able to refute every single point. I mean, there are so many different anomalies when you really get into it. You can get lost in, why does Earth optically look flat? Then you ask, well, what's up with refraction? Then I got into, you will go on your own journey if you're really curious about this. But that's something that's going to really take time on your end that I can't just answer for you right now.
I already did, but thanks. All right, Robert, you going to share your screen?
Sure. Yeah. All right. So you asked the question, how do you go film the ISS going by? First, you go to this website called Transit Finder, and you enter you can basically select it from the map, or you can put your lat long in there, whatever you want to do. This is the window you want to look at. You hit calculate, and it will show you on a map, on this day, the moon is close by. That's good. The ISS is close to transiting. Looking for any. Okay, I think this one's pretty good. So on this day, at 4:45, the ISS is going to cross by the moon. But you can see it's not quite there. It's going to miss. So if I say show on map, I can basically say, okay, well, if I go for a, come on, replay. If I go for a, give me a second here. If I go, here we go. Here's the perfect one. So if I show it on the map, as long as you're in that, anywhere along that path, you know that at that particular time, the ISS is going to cross in front of the moon. So you get your camera out, and give me 1 second here, because I did this a couple years ago with the P900. And you just focus in. Why am I getting commercials? I'm not monetized. Come on. You just focus in on the moon, and you'll actually see, and I recommend video. Do 60 frames per second, the highest quality you can get, because it's going to pass by the moon. This is full speed. You're going to see it go by. That's how fast it went by the moon. Mm-hmm. And I start slowing it down because it goes like, you blink and it's gone by. That's I said 4 times. It's actually a quarter speed.
Oh, and this is with your P900?
Yeah, that's with the P900. That's at max P900
What
zoom.
kind of shutter speed is that working at?
60 frames per second. So I did video.
At video, huh?
Wow. Yeah. So it's fairly easy to do. It was kind of cool. And you'll actually see the ISS coming across the sky. And you'll see it as it passes by the moon. You're like, oh, I got it. And you go back and look at your camera. So that's actually, it's pretty easy to do. It wasn't that bad. And it's kind of cool to see the results. There was a recent one that just came out. This guy captured it, and it was a pretty cool shot, which I'll kind of bring up here. Oh yeah, you can see the individual solar panels and some of the structure of it. And this was just an amateur. He was using a telescope, wasn't using a Nikon camera. Mm-hmm. But that was a pretty cool shot. I just kind of had one last, where to go? Too many darn windows opened up. So did I find it? Done it? And Mike must get set up for his next one. I'm being up closing out windows as I go here anyways. No, not that one. Where'd it go? Not that one. Wow, how many windows do I got open? Holy moly.
Boy. Lots of tabs.
Actually, I'll open a new one. So the you're not military, were you?
No.
Any idea what that aircraft is?
That communications aircraft, right?
Actually, it's a radar aircraft. Yeah. It's an airborne radar platform. I actually got to fly on it when I was in the Air Force. And its primary purpose is to fly up somewhere outside of the, say like Russia's border, or it's flying around, or kind of, there's a Navy version of it as well. And that's a radar dish on top. And the reason they do that is that they can see much further away by getting up to that 30, 40,000 feet. They can see multitudes further than any ground-based radar. So if it was truly flat, there wouldn't really be a need for that aircraft to be able to see over the horizon. If that makes sense.
Well, no, because height, even on a planar geometry, height still gives you further distance to view. So yeah, I mean, it works both ways.
We're running out of time. I mean, maybe we can do this another time, but I did want to share with you, these are some pictures from the most recent Crew 2 return from the ISS. If you want to go out there, I can send you those links, but we don't have time to discuss them, but this was actually a pretty cool shot as they were departing the ISS, and they actually got to fly around it and got some very high fidelity shots. I don't think we're gonna have time to discuss them today, but maybe online we could do it. But
yeah,
some pretty cool stuff in here.
I definitely plan on doing some experiments as much as I can, and I'll keep in touch with you guys, let you know where I'm at.
Yeah, maybe we can do this another time. This was fun. No arguing, no screaming, no people rage quitting. That's the kind of debates I like.
Yeah.
Cool.
Mike, I think I'm gonna head out and do something fun. You still got more work ahead of you?
I have another one. So I have
Yeah.
one more thing. I put it in the chat already. Our Facebook chat from Lael, King of the Flurfs, who's not a Flurf, said, Bradley, if radio waves are limitations. Let's see. If radio waves limitations, why can ham radio people in the center of the United States talk with someone in Central Europe? So something to ponder, I suppose, because we don't have time
Because
to get
it's
into
flat. I don't know.
that. But it's about the limitation.
Yeah.
Right.
So as far as I know, things can only propagate so far. But I have heard ham radios have a ridiculous range, and that's partly why they're pretty much controlled usage. I guess you know, not anyone can just go operate a ham radio now.
Anybody can become a ham
Anybody
radio operator.
And
Anybody.
the test to
Oh.
getting a license is low.
Yeah, it's super
Is
easy.
it?
And the reason ham radios work because they bounce off the troposphere, so they can
Yeah,
actually wrap around the Earth. But
All right. Well,
bouncing off something.
we'll leave it at that. Anything you want to say before we go, Bradley?
No, I appreciate the opportunity to be here, and you know, I again, it's a constant quest for knowledge for me. So appreciate you guys having me on.
yep, in respects to the mic, and it's 11 o'clock there, and he's about to start another one of these, so it's my bedtime.
Yep.
I'm a night owl, so all right, everybody. Thanks a lot. We
Thanks,
will
guys.
see you in just a couple minutes. I think the video is linked in this one. It'll automatically send it to you. So we'll see you in the next one. Bye.
Awesome.
Bye.